Welcome back. So, we will see a principled way of doing it, which is called the gradient boosting mechanism. So, recall that what we need that we have h m of x to be equal to h m minus 1 of x plus alpha m times h m of x. Okay. Goal is to find a new learner h m of x to minimize the risk. Now, let us write that. So, what is the risk, which is mathematically speaking. So, we have I from 1 through n, we have some L, the corresponding loss function yi comma, we need to minimize the loss of hm of x at the mth stage, and the optimization is over h and alpha. We need to find an alpha and an h such that the risk of hm. So, please note that all of these h are hypothesis functions, right. So, we need to minimize this. Is it all right? Mathematically, this is what we need to do at every step. At every iteration, we will have to ensure that this will happen. Please understand the objective properly, because the rest is all algebra. But is this all right? Yeah.
When you say iteration, is it in between the training iterations or each hypothesis after training complete? Like the iteration means.
Oh no, this is like, yeah, this is, you have capital B number of data sets, right. So, on every data set you train a hypothesis. That is the iteration that I am talking about. Yeah. Oh, it is not the iteration within a particular training. So, you are iterating over multiple data sets now, correct. Yeah. Okay. Now, we will have to write this as, consider L of hm. So, what is this? This is equal to, let us slightly abuse the math a little and now consider functions as variables and take derivatives. It is not the exact way to do it, you will have to write the Euler-Lagrangian equations, but I will take that leap and do that. So, this is yeah, what is this equal to? This is equal to L that we are computing at yi comma, what is hm? Hm is, this is over m h m minus 1 times x plus, no there is no sum here, right. Yeah, my bad. This is h m minus 1 x plus alpha m h m, correct. Yeah. There is also an I here, because we are doing it for one particular data point and we sum it over all of them, right. Now, consider this term yi comma hm minus 1 xi plus alpha m hm. This is equal to L that is evaluated at comma h m minus 1 xi plus the derivative of the loss with respect to h times, and this is evaluated at h minus 1 times alpha h. What did I do? What is this? First order Taylor series. I just expanded this term using Taylor series up to the first derivative terms, that is it. And what have I expanded it around? I have expanded it around h m minus 1. So, the above is I have treated this as a function of h and expanded it using Taylor series around h equal to h minus 1. This is all right. So, where did I make that algebraic mistake? So, this h is a function, I am treating that as a variable and taking the derivative, right. So, that is the mathematical incorrectness, but yeah, okay. Now, let this entire derivative term, right, be written as some gi. Okay. If I do that, then my LHS is equal to L yi comma h m minus 1 xi, that is the first term, plus alpha times gi into hi. No, h of xi, sorry. Do you see why there is an index I here for the gradient? It is because we are evaluating that on the sample xi. So, we will have to sum it over all samples, that is why we have this. So, this is what we have as the LHS and we want to minimize the sum of this. Our objective now, again our optimization problem is argmin have to optimize over alpha and h the sum of this particular term L yi comma h m minus 1 xi plus alpha times gi h of xi. Yeah, this is what we want to do. Any questions so far? Okay. So, here the first term, this term, right, is independent of the optimization variable, because this is the loss that we are computing on the ensemble that we have obtained till m minus 1 iteration. We already know what this is because we are standing at mth iteration. This is all right. So, this optimization now is equivalent to minimizing over does it make sense? So, this is the key equation of gradient boosted models. Why are they called gradient boosted? Because the boosting or the aggregation is happening through the gradient computation over the function space. I have still not told you how to solve this optimization problem, right. Do we know how to compute gi, by the way? Do we know how to compute that? We do, because this gradient is being evaluated at h equal to h m minus 1. We know how to do this. So, we know what the loss function is. If you take the loss function and take a derivative with respect to the hypothesis class, then this gradient function becomes a function of yi and xi. And if we are doing it at h m minus 1, we know what the hypothesis is. So, the entire gradient term is evaluated. This can be evaluated. I will show you an example. Okay. So, what is to be done is we will have to find what this h is by solving this particular optimization problem. Is that okay? Any questions here? Okay. So, the next question is how to minimize, okay, let me write that maybe gi evaluated at h equal to h m minus 1 can be computed Therefore, now the question is how to minimize this particular sum. How to do this? So, please note that this product that we want to minimize now is nothing but the inner product between these two vectors. So, if you look into these two as n dimensional vectors, what we are computing is nothing but the inner product. If you have inner product of two vectors, okay, you will have to find h that would minimize this. How would you do this? Which implies the argmin, the minimizer of this inner product over h. What is this equal to? Is the h such that it is just negative of the gradient. So, if there are two vectors and we are looking at inner products, when would the inner product be minimum? If both of them point to orthogonal directions, right. So, when would that happen? If you choose your h to be the negative of gradient at every point, then you would get the hypothesis that would minimize the error. Does it make sense? Okay. Now, how would we ensure that this is done algorithmically? Do you see what is happening? What is happening is we have m minus 1 classifiers and we want to now find the mth classifier, and I am saying that you find the mth classifier in such a way that it is equal to the value of the gradient, this particular gradient that we are computed at every single data point. That is it. It has to be equal to the negative of this particular gradient that we are taking, gradient of the loss with respect to the hypothesis function at every point. You will have to just make your set your h m of x to be equal to this, is what gradient boosted is saying. So, how do we do this? Now, to find h star that is proportional to negative of gi, define hm to be equal to the one that would minimize the some error metric. You can take mean squared error for instance over the negative gradient. See, finding this h star now is a regression problem with the regression labels being equal to minus gi. Did you understand what I am saying? So, please give some attention here. Till here we found out that the optimal h that we have to find at the mth iteration is the one that is proportional to the negative of gradient, or rather this proportionality can be equality also, right, equal to the negative of the gradient at every data point. Is this clear? Is this statement clear? I will repeat it. If you have questions, ask me, because this is very, very important. By looking at Taylor series expansion, we found out that in the gradient boosted algorithms, the optimal hypothesis that you need to be finding at the mth iteration is the one that is equal to the value of the gradient, okay, at every x, is what we found out here. Is this statement clear? And what is this gi? Gi is this particular thing which can be computed. Do you see? All of you clear here? Because this is very important. I mean, maybe take a minute and tell me if you understand this or not.
Sir, aren't we taking the average lambda all the samples take for one data point? How does it reflect in the entire hypothesis?
No, the hypothesis has to be equal to the gradient at all data points is all we are saying. How do we do that is the next question will come. Did you understand the statement and the math? The math is telling you that you will have to find your mth hypothesis such that it is equal to this particular gradient at all data points is all it is asking for. Is this clear? Because this is often the the point of confusion when we are looking at the gradient boosting trees, because note that we are still solving a classification. Even if we are solving a classification problem, our h has to be equal to the negative of gradient at all data points. That is how it has to be because of this math. So now how do we do this is this question which we will see in a while, but is the math clear so far? Yeah.
The loss taken over the sample data set or the original data set?
The loss is taken over.
The loss here
Uh-huh.
is taken over the sample data set or the original data set.
See, this loss is being computed on the data set which you are using to find the mth classifier, which can be the sample data set, which will be the sample data set. Okay. Any other questions? Now the next question is that how do we ensure that the classifier is equal to that particular gradient value at all possible x is what you asked. Treat that as a regression problem. So now all I am saying is to find HM at the mth stage, you will have to solve a regression problem by keeping negative of gradients as the labels. That is it. So therefore, to find h star that is proportional to g minus gi, right, you will have to solve a regression problem with minus gi as labels. How do you solve, what loss function do you use to solve a regression problem? That is exactly what I have written here, mean squared error, where these are your labels. This is yi minus hx squared, right? This is your regression problem. Now the labels are negative of the gradient. Is that all right? Okay. Now the if I have to write an algorithm for gradient boosting, how do I write it? So the final gradient boosting algorithm is as follows. Okay. Now given a data set D, start by creating B data sets. So you do a sampling with replacement. Now for small b or m equal to 1 2, so b minus 1, do the following. Hm of x is equal to h m minus 1 of x plus some alpha times hm of x. So please note in naive gradient boosting, alpha is a hyperparameter. We do not optimize over alpha. But in the next algorithm that we will look at, which is AdaBoost, we will optimize over alpha as well, and we will find out what the optimal alpha is as well. compute minus gi I want two indices, that is why I just got stuck. So, this is we will have to find this gradient for the mth iteration for ith sample as the negative of h of xi divided by h xi evaluated at hm minus 1 often in literature, right, this is also called as residual. People call this as residual. Yeah, this is called residual. Okay, the derivative of the loss function with respect to hypothesis. Please note that this derivative, see, we were looking at this derivative with respect to the parameters so far for gradient descent, standard gradient descent, right. So, here we are looking at the derivative of this loss function with respect to the hypothesis itself. Okay. Now, there is one missing piece that I have not told you. I was waiting if some of you will ask that question. How do we find this derivative? Right. Suppose your loss function is, or rather, okay, let me tell you, this loss function is a function of y and h, because that is how we define the loss function, right. So, treat that h as a variable and they just take the derivative, that is it. I leave this as a homework. Please find out what would be the form of this residual for different loss functions. Suppose the loss function is squared error loss function. So, what would be the form of this? Can somebody quickly tell me what would be the form of this for squared error loss? It will be y minus hx, which is actually the residual, right. It is the difference between the true label and the outputs. That is why the name residual, the negative of the gradient is the residual. If you take the cross entropy, just see what happens and so on, right. You compute this, and this can be computed because we have h of hm minus 1 and we also know what the loss function is, that can be evaluated. Compute this, and then what should we do next? So, we have to compute this for all samples, train hm of x by regressing over gm, negative of gm. Correct. Please note that I have left the superscript here, right, the subscript I here. Why? Because I am doing it for the entire data set. You will have to compute the residual for every data point, okay, and once you do it for the all data points at a particular iteration, use that and regress, find the next set of classifier by regressing over gm. It's all right, and then get hm of x to be equal to, take the previous one that we already have, that is it. You get the next classifier, you move on. This is the gradient boosted tree algorithm. Yeah, good question. How do we initialize it? Initialize this is that you can either take data set and train a classifier and that will be your initial classifier, right, or you can randomly initialize as well, it does not matter, but we are assuming that all the individual classifiers are better than chance, right. So, it is better to initialize it with some classifier that you train on some data, right. So, the first iteration is how you do it. This okay? Now, if you regularize this, suppose we use, okay, by the way, never in the gradient boosting algorithms we restricted the form of HM. You can find an ensemble of neural networks by using this algorithm. So, there is nobody stops you from doing that, correct. You can actually find this, but if you use decision trees, see decision trees as we saw were those algorithms which are quick to build, but they are high variance. So, all these techniques are reducing the variance as we saw. That is why typically the ensembling are done using trees as individual classifiers, and if you use trees as individual hypothesis in a gradient boosting algorithm, then it is called gradient boosted trees. Okay. Now, going one step forward, if you regularize the trees in a particular manner, so here there is no regularization over the individual hypothesis on the parameter space, and if you do it in terms of restricting the number of nodes in a particular depth and all that, we saw multiple ways of regressing the decision trees, right. If we do that and also consider the second order term when you are expanding the Taylor series expansion, it was observed empirically that it will give you better reduction in the error compared to a first order gradient boosted tree, and that particular algorithm is what is referred to as XGBoost, extreme gradient boosted models. It is basically using the second order gradients and regularizing the trees explicitly. So, XGBoost is one of the go to algorithms for a lot of the industrial applications, because it is very quick to calculate, and it is exactly doing this, it is iteratingly finding it. It is a boosting algorithm. The individual hypothesis functions are trees, okay, and they are done in such a way that they are regularized at every step, is what XGBoost is all about. Okay. Okay, so now there is any questions here?
Since we are in some method itself, we are reducing the variance. So this itself is regularization.
It is definitely regularizing that way, yeah. But here, right, we are doing it in a better way. We are iteratively doing it, and we are ensuring that the minimization is, see, in the bagging case, okay, so now since you made this point, it's a nice point. In the bagging case, there is no guarantee that the next classifier or the other classifier that you learn is improving over whatever bagging that we have done so far. I mean, it is not even iterative, but still if you assume that, okay, you are training one classifier at a time, there is no way that your new classifier that you learn is trying to undo the mistakes that the previous classifiers did. But here you cast the problem itself in such a way that the new classifier that you add to the ensemble is built in such a way that it is undoing all the mistakes that the previous classifiers have done till this point. That is what I mean in the when we started the discussion on boosting, I told you that this is a principled way of finding the next classifier in the ensemble. And what is this principled way? In the sense that you ensure that the next classifier that you get is always better than the ensemble that we have so far. That's how we are doing it. So, this is gradient boosted trees, and I told you that we can optimize over alpha as well. So far we have not optimized over alphas. What happened is that there is another algorithm called AdaBoost, which was considered as the pinnacle of boosting algorithms. It was extraordinarily designed. I think 95 is when it came, and that was designed independently of gradient boosting. Okay, it is an algorithm, and people gave the statistical learning theory or ERM explanation so as to why AdaBoost algorithms will do better. Now, after gradient boosting came, it was shown that AdaBoost is actually one particular way of doing gradient boosting on a particular loss function, right. So, now that we have looked at gradient boosting, so I will write down the AdaBoost algorithm, okay, and tell you what it is algorithmically, and then we will show that these algorithms are exactly realization of the gradient boosting algorithm is what we will do, okay. So perhaps we will do it in the next class, and that finishes our ensemble learning, and then we will go to the unsupervised learning methods, the PCA and the other embedding extraction. I told you that I will also talk about the self supervised learning techniques in the coming classes. We will do that in the next class. Okay, thank you.